శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో ఎంబీఏ, నాక్ ఏ గ్రేడ్ మరియు ఐఎస్ఓ సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతుంది. 2014లో ఐఎస్ఓ గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే ఏ గ్రేడ్, 2016లో నాక్ ఏ గ్రేడ్, ఇప్పుడు ఎన్బీఏ సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning. Good morning. Here we are going to start the unit 3, that is analysis of linear systems. Analysis of linear systems. Here the contents of these topics are introduction about the linear systems, what is meant by linear system, what is meant by impulse response, what is the response of linear system, linear time invariant, that is LTI systems, linear time variant system, that is LTV system, concept of convolution in time domain and frequency domain, graphical representation of convolution, next transfer function of LTI system, linear time invariant system, then related problems on the above topics. Next, filter characteristics of linear systems. What are the filter characteristics of linear systems? Next, distortionless transmission through a system, signal bandwidth and system bandwidth. Next, ideal low pass filter, ideal high pass filter, and ideal band pass filter characteristics. Then causality and polywinar criteria for physical realization. Then relationship between bandwidth and the rise time. Here in this topic we are going to discuss about all these topics. Okay. Next, what is meant by the linear system, right? Here in analysis of linear systems, generally systems, if you take system, what is meant by system? What is the relation between signals and systems? It will take several signals as inputs, it processes something and it gives several signals as outputs. That is system is one which processes the signals and gives the same signals as the outputs, which processes the signal and gives some output. Here the output and input may not be equal. So here the systems are classified into linear, non-linear, time variant and time invariant systems. Linear systems, non-linear systems, time variant systems and time invariant systems, right? So what is meant by linear system? If you take any linear system, okay, system is one which will take the input signal f of t, and here the output signal is r of t, right? In the see this diagram, f of t is the input signal, r of t is the output signal. What is meant by linear system? Linear system is one which satisfies the scaling and superposition theorem, okay, which satisfies the scaling theorem and superposition theorem, or scaling property and superposition theorem, okay. So and its output changes linearly with the change in output. If you change the input, output is also changed. If you does not change the input, the output will not change, okay. So there is a linearity between the input and output. If you change the input linearly, then the output will also change linearly, okay. Let us take the system having the input f of t and the output r of t. So f of t tends to r of t and some constant k into f of t tends to k into r of t, then this relation shows the scaling property. What the scaling property states that if input signal relates to the output signal, or some constant into input signal relates to some constant into output signal, then this relation shows the scaling property. Then if f1 of t relates to r1 of t and f2 of t relates to r2 of t, then f1 of t plus f2 of t relates to r1 of t plus r2 of t. Here we are taking two different systems, right? So F1 of t and F2 of t. These two are the inputs for different systems. Similarly, R1 of t and R2 of t. These two are the corresponding outputs for the different systems. If F1 of t tends to R1 of t and F2 of t tends to R2 of t, then F1 of t, we are adding these two inputs, F1 of t plus F2 of t tends to outputs R1 of t plus R2 of t. This relation shows the superposition property or superposition theorem. On the whole, that is by combining the above properties, that is scaling property and superposition theorem, it gives the linearity property, which is defined as alpha into f1 of t plus beta into f2 of t relates to alpha into r1 of t plus beta into r2 of t, where f1 of t and f2 of t are inputs and r1 of t and r2 of t are outputs, right? How the linear system is defined, how it is, why it is called linear system. There is a linearity between input and output. If you change the input, output will automatically changes. There is a linearity between the input and output, or it satisfies the scaling and superposition theorems, then it is said to be linear system. Here we are taking the system having the input f of t and the output r of t. If f of t is related to r of t, or some constant into f of t is related to some constant into r of t, then this relation is called scaling property. And if f1 of t relates to r1 of t and f2 of t relates to r2 of t, then f1 of t plus f2 of t relates to r1 of t plus r2 of t. This property is called superposition property. So by combining these two properties, what are those two properties? Scaling property and superposition property. It gives the linearity property, that is some constant alpha into f1 of t plus some constant beta into f2 of t, which is related to some constant alpha into r1 of t plus some constant beta into r2 of t. This is linearity. This is called what we call as a linear system. This is what we call as linear system. Then time invariant system. What is meant by time invariant? So these are the different types of systems. So what are those types of the system? These are classified into linear system, non-linear system, time variant system, and time invariant system. What is meant by non-linear system? There is a non-linearity between the input and output signals. Non-linearity means if you are changing the input, the output does not change. If you are not changing the input, output may change. So this is called non-linear system. There is no linearity between the input and output signals. The system does not obey the scaling property as well as superposition theorem. Then it is called the non-linear system. Okay, then coming to the time variant system. What is meant by time variant system? Yes, coming to the time variant system. The system whose parameters do not change with time is called time invariant system. Okay, time invariant system means the system parameters, the system whose parameters does not change, do not change with time. With respect to time, the parameters will not change. Okay, with respect to time, the parameters will not change. Then that is called time invariant system. What we call as time invariant system. Okay, so it is called time invariant system. It is defined like this. If f of t tends to r of t, then f of t minus tau, here we are changing the time to tau units. Here we are shifting the time to tau units. So f of t minus tau relates to r of t minus tau. The system which is linear and time invariant is called as linear time invariant system, that is LTI system. Linear system. Linear system means which obeys the scaling property as well as a superposition property. So by combining these two properties, then we can say that the system is linear system. So a system which is linear and time invariant, here we are adding two properties or two systems, linear system as well as time invariant system. By adding these two, it will become linear time invariant system, that is also called as LTI system. LTI system. So what is meant by time invariant system? The system whose parameters do not change with time is called time invariant system. So f of t tends to r of t. F of t minus tau tends to r of t minus tau. Okay, this is called time invariant system. By adding linear system and time invariant system, it will become linear time invariant system, or it is also called as LTI system. Okay, then coming to the properties of LTI systems, we have four properties of LTI systems. What is meant by linear LTI system? That is linear time invariant system. Linear time invariant system. Okay, linear time invariant system. Okay, right. So it has some properties. What are those properties? Here we have four properties are there. Those are cumulative property, distributive property, associative property, and last one is static and dynamic property. First one is cumulative property. Second one is distributive property. Third one is associative property. And fourth one is static and dynamic property. What is meant by cumulative property? Cumulative property. Here we are considering the system having the impulse response h of t. Impulse response is denoted by h of t. Okay, and it is having the input f of t and output r of t. Then the output r of t can be expressed from the above diagram as the input f of t convolved with the impulse response h of t. The convolution is represented by the star mark here. Here star mark is there. So f of t star h of t, or we can write this as h of t star f of t. This is called cumulative property. So here we are considering the system with impulse response h of t having the input signal f of t and the output signal r of t. Then this r of t can be represented as the convolution of the input signal and impulse response, that is f of t convolved with h of t, or we can write this as h of t convolved with f of t. This is cumulative property. Next one is distributive property. What is meant by distributive property? So here it will distribute something. Okay, so let us take the system having the impulse responses h1 of t plus h2 of t. We are adding these two responses h1 of t and h2 of t, having the input f of t and output r of t. Then how this distributive property is defined as r1 of t is the output, first output. If we take r1 of t, then it will be represented as f1 of t, f1 of t convolved with the impulse response h1 of t, and r2 of t can be represented as f2 of t convolved with the h2 of t. Okay, then we add, by adding these two, r1 of t plus r2 of t, it will become f1 of t convolution with h1 of t plus f2 of t convolution with h2 of t, right? So here f of t is common here, so taking common as f of t convolved with h1 of t plus h2 of t. So this is called, this is nothing but the distributive property. Okay, so r1 of t plus r2 of t is equal to f of t convolved with h1 of t plus f of t convolved with h2 of t. Then by taking f of t as common, f of t convolved with h1 of t plus h2 of t, this is nothing but the distributive property. Distributive property. Then third one is associative property. What is meant by associative property? Here if r1 of t is represented as f of t convolved with h1 of t convolved with h2 of t, f of t convolved with h1 of t convolved with h2 of t, then r2 of t can be defined as f of t convolved with h1 of t whole thing convolved with h2 of t. Similarly, r3 of t can be defined as f of t convolved with h2 of t whole convolved with h1 of t. This is nothing but associative property. Associative property can be represented like this. We can write at any way. Write f of t. Here f of t is converted with the combination of h1 of t convolution with h2 of t. Okay, this can be written like this: r2 of t is equal to f of t converted with h1 of t whole converted with h2 of t. R3 of t can be represented as f of t converted with h2 of t whole converted with h1 of t. This is associative property. Next one is static and dynamic property. Static and dynamic property. What is meant by static systems? So static systems are generally memoryless systems. These systems does not have any memory. Okay, so the output depends only on the present input signal. In these systems, impulse response h of t is 0 for t is less than or equal to 0. Static systems are memoryless systems. There is no storage. There is no storage in these static systems. That's why we are called these static systems are memoryless systems. Okay, that means the output depends on the present value of the input. The output depends on only on the present input. So the impulse response h of t is 0 here. Here the impulse response h of t is 0 for t is less than or equal to 0. Then coming to the dynamic systems are one whose output depends on the present and past inputs. Present as well as past inputs. That is y of t is equal to x of t plus x of t plus 1, like that. Okay, x of t plus x of t plus 1. X of t is present input, x of t plus 1 is past input. Okay, right. So these are the four properties. What are those four properties? Cumulative property, distributive property, associative property, static and dynamic property. Cumulative property is nothing but r of t can be represented as f of t converted with h of t or h of t converted with f of t. Next one is distributive property can be defined as r1 of t plus r2 of t can be represented as f of t converted with h1 of t whole plus f of t converted with h2 of t whole. So by taking f of t as common, f of t converted with h1 of t plus h2 of t whole. Then associative property. Associative property can be represented as r1 of t is equal to f of t converted with h1 of t converted with h2 of t. These can be modified as r2 of t is equal to f of t converted with h1 of t whole converted with h2 of t. R3 of t is equal to f of t converted with h2 of t whole converted with h1 of t. Then static and dynamic property means static property or static systems are memoryless systems. So here the outputs are what depends on present input values. So impulse response is 0 for t is less than or equal to 0 for static systems. For dynamic systems, these present the outputs are depends upon the present inputs as well as past inputs. Okay, so these are the properties of LTI systems. What is meant by LTI system? Linear time invariant system. It is linear as well as time invariant. Okay, so these what is meant by time invariant? Parameters do not change with the time. Then these are called time invariant systems. Okay, time invariant systems. So and these are the properties of our LTI systems. Next, coming to the transfer function of LTI system. It is also called as a system function, transfer function or system function. Generally, transfer function means in simple way we can say that a transfer function is nothing but output by input. For the system, if you take any system, it has both input as well as output, right? So transfer function can be defined as output by input. Here, consider an exponential signal to be applied to a linear time invariant system. Okay, exponential system. An exponential signal is applied to a linear time invariant system. Then its response is given as, let us take the response of the exponential signal to be applied to a system is y of t is equal to x of t convoluted with h of t. Here, what is x of t? X of t should be a exponential signal, that is in the form of e power j omega t, right? Exponential signal means e power j omega t. So x of t here is e power j omega t, and its response, impulse response, h of t. H of t is its impulse response. Then y of t can be defined as x of t convoluted with h of t. The convolution formula is this one. Integral minus infinity to infinity h of tau into x of t minus tau d tau. This is actually tau, h of tau. Okay, h of tau. So it is integral minus infinity to infinity h of tau into x of t is e power j omega t. X of t minus tau is replace t by t minus tau. So e power j omega t minus tau d tau. Okay, integral minus infinity to infinity h of tau into expand this e power j omega t into e power minus j omega tau d tau. Right? Extract e power j omega t to the outside. So e power j omega t into integral minus infinity to infinity h of tau into e power minus j omega tau d tau. Then it is nothing but the Fourier transform. This is the Fourier transform of h of tau, that is h of omega, e power j omega t into h of omega, right? So y of t is x of t into e power j omega t is x of t into h of omega. Let it be considered as equation number 1. Is it clear up to now? Here we are considering a system, linear time invariant system, whose input is an exponential signal. Exponential signal is in the form of e power j omega t. So whose input is an exponential signal. So x of t is e power j omega t. Okay. Its impulse response is h of t, so that y of t becomes x of t convolved with h of t. X of t convolved with h of t as the formula integral minus infinity infinity h of tau into x of t minus tau d tau. Okay, that is x of t is e power j omega t, then x of t minus tau will become e power j omega t minus tau, right? Okay, then integral minus infinity to infinity h of tau into e power j omega t minus tau d tau, right? So expand this e power j omega t into e power minus j omega tau, extract e power j omega t to the outside. So e power j omega t integral minus infinity infinity h of tau into e power minus j omega tau d tau. This is nothing but the Fourier transform of h of tau, that is h of omega. Okay, e power j omega t is nothing but x of t, right? So write this one as y of t equal to x of t into h of omega as equation number 1. Equation number 1. Then where h of omega is equal to integral minus infinity to infinity h of t into e power minus j omega tau d tau, or h of t. How to get h of t? H of t by taking inverse Fourier transform of h of omega. Okay, inverse Fourier transform of h of omega, that is 1 by 2 pi into integral minus infinity to infinity h of omega into e power plus j omega tau d tau, right? This is a Fourier transform. Fourier transform. This is inverse Fourier transform, right? Inverse Fourier transform of h of omega. By taking inverse Fourier transform of h of omega, we will get h of t, right? So thus, the above equation states that the response of a linear time invariant system to complex exponential function of frequency omega is same as the input multiplied by a constant called transfer function h of omega. So it is 1 by 2 pi integral minus infinity infinity e power j omega tau d tau is nothing but complex exponential function of frequency omega. Okay, response of, that is the response of a LTI system, linear time invariant system, to complex exponential function of frequency omega is same as the input multiplied by constant. That is constant. What is that constant? H of omega, h of omega, h of omega. That is called transfer function. H of omega is called transfer function. Okay. So the transfer function h of omega is given by h of omega equal to output signal y of t by the input signal x of t, output signal y of t by input signal x of t at x of t is equal to e power j omega t. Okay, see here equation number 1. See the equation number 1. It is equal to x of t into h of omega, or h of omega is y of t by x of t. At x of t equal to e power j omega t, right? So this is called our transfer function. Transfer function h of omega is equal to y of t by x of t at x of t is equal to e power j omega t, e power j omega t, right? If we express input in terms of its Fourier transform, then x of t is equal to x of t, uh, how it will become x of t is e power j omega t, right? So in terms of Fourier transform, then it is equal to 1 by 2 pi integral minus infinity to infinity x of omega into e power j omega t d omega. Substituting this x of t in equation number 1, what is that equation number 1? Y of t equal to x of t into h of omega, right? So substitute this equation, x of t equation, Fourier transform expression of x of t in equation number 1, that is y of t becomes 1 by 2 pi integral minus infinity infinity x of omega into e power j omega t d omega into h of omega, right? So uh, one by writing this by above the expression like this, 1 by 2 pi integral minus infinity infinity x of omega into h of omega into e power j omega t d omega, or we can write this product x of omega into h of omega as y of omega, then it will become 1 by 2 pi integral minus infinity to infinity y of omega into e power j omega t d omega, where y of omega equal to x of omega into h of omega, or h of omega equal to y of omega by x of omega. This is the transfer function in frequency domain. Okay, this is the transfer function in frequency domain. Here all the parameters are frequency. This is omega. What is omega? Omega is angular frequency, right? So here all the parameters are in frequency domain, whereas here h of omega equal to y of t by x of t. Here these are in terms of time domain. Okay, so why? Because here we are writing the x of t as the Fourier transform, in the Fourier transform. So x of t is nothing but inverse Fourier transform of x of omega, right? So that is 1 by 2 pi integral minus infinity to infinity x of omega into e power j omega t d omega. So we are simply substituting this value in equation number 1, that will become 1 by 2 pi integral minus infinity to infinity y of omega into e power j omega t d omega, where y of omega is nothing but x of omega into h of omega, or h of omega equal to y of omega by x of omega. This is the transfer function in frequency domain. Okay, next we will discuss about the impulse response. What is meant by impulse response? Impulse response. What is meant by impulse response? See here, let us consider the system having the input signal x of n and output signal y of n. So the response of the, here remember, output signal or response, both are same. The response of the above system, that is nothing but response is nothing but output signal. So the response or output of this system, that is y of n, is equal to transformation of x of n. Okay, transformation of x of n, where y of n is output signal, x of n is input signal, and capital T is a transformation operator. Okay, transformation operator. We can write this response or output signal y of n as a transformation of the input signal, right? Here the input will be transformed to get the output signal. So system will take input signal x of n, it processes something, and it will give the output as y of n. That is nothing but y of n, our response, our output signal is nothing but the transformation of the input signal, right? That's why capital T is called transformation operator. Okay, next, input to the linear time invariant system is unit impulse. Suppose if x of n is unit impulse, how the impulse function is defined? As we already know that impulse function exists only at t equal to 0, at t equal to 0 or at n equal to 0, it exists. At remaining places, its value is 0 only. Okay, right. Here we are taking the input of the linear time invariant system as unit impulse. Okay, unit impulse, that is delta n equal to 1, right? So x of n is equal to delta n, or y of n becomes transformation of delta n, is it not? Transformation of delta n. So the response y of n is impulse response, right? Impulse response. We know that the input signal x of n can be represented in terms of weighted impulses. Weighted impulses, that is y of n can be represented as transformation of x of n. That is nothing but the representation in terms of weighted impulses. Okay, right. Then y of n is equal to, in terms of weighted impulses, we are representing this in weighted impulses. So x of n can be represented as a transformation of sigma k equal to minus infinity to infinity x of k into delta of n minus k. Okay, so sigma transformation of sigma k equal to minus infinity